Water balance is a central organizing theme of hydrology. We use it to think about how water moves around the landscape. It's a basic principle that we use to develop models, and it's important for understanding field data as well. The water balance principle comes from physics, where we have the conservation of mass. The basic approach is to identify a control volume. Basically, this involves drawing a boundary around the region that we're interested in. Then we identify all the ways that mass is going to cross into this control volume, the ways that the mass crosses out, and then how mass is stored within this control volume and how the mass stored in there changes. And so we can apply this, or we can write this like so, that the mass in equals the mass out plus the change of mass within the control volume. So that's our basic conservation of mass. We can apply a time derivative to it, to the whole thing, and that's going to apply to each one of these terms. And when we have the rate of change of these different terms, that converts the mass in to the rate of mass in. So the conservation of mass principle can also be written like this. The rate of mass in equals the rate of mass out plus the rate of mass stored. And here I'm using this symbol delta to mean change. So in the first line it's the change of mass stored, and then in this second line it's the rate of change of mass stored, or the change of mass stored per change in time. So this would be one way to think about it. This is another way to think about it. And we can say that, well, over a long period of time, or perhaps under some other circumstances, the mass that's stored within this control volume is not changing. Maybe over a long period of time, what happens is that it may change over short periods, but over the long period of time, those changes may just average out. So the inflows are equal to the outflows, and the change is negligible over a long period of time, in which case this term here is going to be equal to 0. So if that's the case, then we have the rate of mass in equals rate of mass out. And there's no change in storage, and this is what we mean by steady state. So if we have a system that's at steady state, then the mass change within it is equal to 0, and the rate in equals the rate out. Okay, so we can make a change from this. We've done the mass conservation, but we'll typically in hydrology not use mass. And what we're going to do is say that this is true. So mass, this is just from the previous page, mass rate in equals mass rate out plus the change of mass stored with time. Now, if we divide both sides by the density of water is the mass per volume. So if we divide both sides, then we still have an equation, but the density is mass per volume, and so the masses cancel out. And so if the density stays constant throughout our process, then the mass balance gives us a volume balance. And we have the volumetric rate in equals volumetric rate out plus the change of volume stored with time. So that's our volume balance, and we can still say that over a long period of time the variations may balance out, or for some other reason we may have a condition of steady state where there's no change of volume stored, in which case the volumetric rate in equals the volumetric rate out, and taken like that, that's what we mean by steady state for a volume balance. Okay, so the key to having a volume balance work is that the density stays constant through the problem. And for many cases in hydrology, we're interested in water, and water density, water density certainly can change. There certainly are situations where it can change, but for many of the things we're interested in, we can assume that it's going to stay roughly constant, and so we can take the principle of mass balance and then derive, or then basically reduce it to the principle of a volume balance. Okay, so what we've seen on the previous page was that volume rates, volume as a function of time, that we'll call a volumetric flow rate, and it'll have units of volume per time. We'll write that in terms of a gallon per minute, or a cubic foot per second, or perhaps a cubic meter per second. We might also write that like so. So this is a convenient way to describe a flow in a particular structure. A stream, for example, flow rate in a stream is typically described as cubic feet per second, at least in this country. If we have flows in pipes, in a hose, then it makes sense to use volumetric flow rate. But in the subsurface, through an aquifer, for example, we don't really have a well-defined structure for the flow to go through. And so in that case, we'll define the volumetric flow rate on a per area basis. And that'll give us the flux. So here's a little demo of flux. Here's some volume, and it's going to move through a given area. And so the volume that moves through a given area in a given time, that's the volumetric flux. It's related to the volumetric flow rate, where we have the volumetric flow rate divided by the area. Well, I guess we can see this right there. That's a volumetric flow rate. So the volumetric flow rate divided by the cross-sectional area through which the flow is going, that's also a volume flux. Okay, so let's see. We've got volume per area per time. That'll have units of length cubed is a volume per area, length squared per time. So that has units of a length per time. This is the same unit as a velocity, but we recognize that this has a different meaning than velocity, even though it has the same units. As it turns out, the velocity through a stream, in a stream or in a pipe, the average velocity will be equivalent to the flux. It'll be equal to. However, if we measure the flux through a material that is partially obstructed, so the flow is not filling the area that we're using to determine the flux over, in that case, the flux will be greater than the flux will be less than the velocity. The velocity will be greater than the flux. Okay, so we've just seen how volumetric flux works. We also can have a mass flux, which would be a mass. So this would be mass going through a unit area in a unit of time. We could also have energy flux, energy going through a unit area in a unit of time. So we can have fluxes of really many different things, and in every case we have a flux of mass or energy, or um, could have a flux of anything, of dogs, and it'll be whatever is fluxing going through a unit area in a unit of time. So we always have this down in the denominator. Okay, so what we want to do now is take a look at how the conservation of mass can be written in terms of the flux. And what we saw a couple of slides ago is that if the density is constant, then we can think of conservation of mass as a conservation of volume. So we've got this. We've got a volumetric rate in is volumetric rate out plus the change of volume stored within our control volume. So I'm going to write this like so. And here's the control volume. So I've got some Q in and some Q out and some volume stored in here that's changing. Okay, so I'm always going to use capital Q to mean a volumetric rate, and little q will be a flux, a volumetric flux. So I could write this like this: Q in times the area in equals Q out. So the flux out times the area out plus, I'm going to call this, let's just say conceptually that the volume stored in here is some depth of water, H, times some area here, cross-sectional area. So it'll be a change of water depth times the area over which it's stored per time. Okay, so we've just taken this volume balance equation and written it here in terms of fluxes and areas through which the flux is occurring. Okay, so fair enough, that should be straightforward. Now, if we have a special case where the area through which the flux is coming in is equal to the area through which the flux is going out, and that's equal to this area of storage, if that's true, then all the A's are equal and they cancel out. So if this is true, then we have this: the flux in equals the flux out plus the change of water depth with time. As it turns out, there'll be a couple of ways that we can write this change of storage, but conceptually this is how we're doing it this time. Okay, so what we have now is the volume balance, the water balance, written in terms of flux. But we have to keep in mind that this only applies for this special case where these areas are the same. Now, in many cases we can kind of manipulate the problem so that we have the areas being the same, but we have to keep in mind that that's going to be necessary. We can't just take any fluxes, because this is the volume balance equation here. It's written in terms of volumetric rates, and so when we convert it and apply it to fluxes, we have to keep in mind that we're doing this. So as an example, we can take a look at the volume balance or the water balance over a continent, and those data are shown up here. And so what we've done is to draw the control volume around the continent, and the fluxes coming in are the precipitation, and coming out there's ET and there's runoff. Now, precipitation and ET are measured typically as volumetric fluxes distributed over the landscape area, say. Runoff, though, this is the flow rate in streams and rivers, And so that's how the water is, that is a way that water is leaving the continental landmass. And this is typically written as or described as a volumetric flow rate. So we can do two things. We can write a volume balance where we convert these two to volumetric rates by, say, taking the precipitation and multiplying by the surface area of the continent. Or we can do this in terms of fluxes, where P and evapotranspiration are fluxes, and we take the runoff as a volumetric rate, and that equals, well, we can convert that to runoff as a flux, where we would divide the volumetric rate of the runoff by the area of the landmass. Okay, so let's take a look at some of the data here. Here is inflows, and this table is written so that on the left side of this line we have all the inflows, and on the right side we have all the outflows. And in general, I always write balance equations like that, where on the left side you have what's in, on the right side you have what's out, and the change in storage. Now, this is at a large scale, continental scale, and over a long enough period, so we're going to ignore the change in storage and just assume these are steady conditions. So what we have is this much, say, for the continent of Europe. Here's how to read this table. The continent of Europe, we've got this volume coming in, 8.3 times 10 to the third cubic kilometers. If we take that and divide by the area of Europe, then we got this many millimeters distributed over the area. And coming out, we have this volume of ET and this volume of surface runoff, or flow in streams. And if we normalize those by the area, we get that many millimeters, that many millimeters. Okay, so that's the basic balance, that the precipitation in, let's say 790 millimeters coming in, is going to equal 507 millimeters, about half a meter, coming out of evapotranspiration, and 283 millimeters of evapotranspiration, or of runoff, I'm sorry, coming out. Okay? So one thing too that I'm showing in this table is the ET written as a fraction of precipitation. So in all cases, the precipitation here is the way that water is getting in. So what we're interested in, I guess, is how much of it is coming out as evapotranspiration and how much of it is coming out as runoff. So what I've done here in this column is normalize those fluxes, the ET and the runoff, to the precipitation coming in. And so in Europe we have 64% of the precipitation is being removed as runoff, and 36% or 0.36 as a fraction is going as runoff. So we've got now the rest of these continents. These are here are all the continents down to here, and then the last row is a summary. And what we can do is just scan through these numbers and take a look and see how the different continents are behaving. And if we just look at precipitation, we can see that, well, let's take a look down here at the averages. So 800 millimeters is the average precipitation on the continents. And if we look at then the various different continents, we can see that many of them are quite close to the average. The anomaly is South America, and it's nearly twice the average. And then Antarctica, and it is also an anomaly. It has a very small amount of precipitation. And if we look at ET out, the average ET out is 45, about half a meter of evapotranspiration over a year. And if we scan down and look for the anomalies there, this one, this is high. This is South America, so we've got a high amount of evapotranspiration, and that seems reasonable because we've got a high amount of rainfall. In Antarctica, we've got a low amount, essentially negligible ET. But we get a bit of a different result if we look at how the ET is done on a fractional basis. That's the worldwide average, that about 60% of the precipitation is removed as evapotranspiration. And if we look at how that's distributed worldwide, we see here is the anomaly, Africa. So Africa has an anomalously large fractional amount of ET compared to the other continents. And that, I think, makes sense because much of North Africa is a desert, and all the other continents are pretty darn close to the average, except for Antarctica, and it's essentially zero. So if we look then at runoff, average is about 0.4, and Africa is low, Antarctica is high, and all the others are about the same. We can also take a look at the volume balance, the water balance on our home state here of South Carolina. I've written it in table form where this is the inflows and this is the outflows. So if we take this as the control volume, we've got some rainfall coming into the state, but if we take this as the control volume, this is just the state border, then we have a river right along this border, and there's a divide. I think this is pretty much the divide up here, but we have some rivers that cross into the state right here. So the inflows are precipitation, but we also have to include rivers flowing in from North Carolina. So here it is represented as a flux, and here's the total inflows as fluxes in inches and millimeters. So rainfall in South Carolina is typically averaged over the state about 4 feet of rain in a year. And the outflows, we've got ET coming out, so that's going to be that'll be happening everywhere except Antarctica. We also have runoff to the ocean, so we've got streams flowing into the ocean, and we have aquifers discharging to the ocean. So the coastal aquifers will discharge in the subsurface to the ocean. And here's the amounts. The amount of ET is 34 inches, and taken as a fraction is 61%, or 0.61 as a fraction, and that's equal to the global average. So the ET in South Carolina is equal to the global average. The runoff to the ocean is that much, and we have just a small fraction, about 1% of the water flowing into flowing from the aquifers, groundwater basically discharging to the ocean. So there's the water budget for South Carolina. And the beauty of this approach is that we can apply it over all scales. We can take this down to the pore scale, and we can apply the balance over the pore scale. We can also do it, though, over more like watershed scales, several acres or hundreds of acres, and apply this and use this to try to understand how water is moving over those smaller scales.